and the convenience on our website, the WOW Challenge website. And if any questions come up, feel free to always contact me with any questions you may have with the challenge. So first of all, introduce myself. I'm Eric Salna, Associate Director with the International Hurricane Research Center and with the Wall of Wind also. And we have Dr. Zisas with us today, who is also with the Wall of Wind research team, and he's going to present a PowerPoint that's going to talk about the science behind the competition and what this year's competition is going to be. So today is February 20th? 21st? 21st. Moving into next week, I'll be updating our Wall of Wind webpage more and more and more. So if you periodically go back, you'll find additional information. The first piece of information that I'll be putting on there is the official entry form. So as we move forward, I'm going to now have every school fill out an entry form. So we have that. And I'll be putting on there more details about the different components of the challenge. And it turns out that this year, there's actually going to be the 4 components. We have the video, and we're going to have a technical paper, and there's going to be an oral presentation, and then the physical test. The videos are coming in now, and the papers will be due, I believe I put the date like the Monday before the challenge. And all of them will be due by email, and then we will grade the papers. And then actually here at FIU is where the teams will come and do their oral presentations live and do their physical test live. And that'll all be judged live during the event. Everyone comes roughly around 8 o'clock, 9 o'clock latest, and then we start the competition. And then there's lunch, and we tally up all the scores, and we know who the winners are immediately. So the trophies are given out right then that day. So we know who's first, second, and third on the day of the competition. You can have as many students as you want on your team as you prepare. But on the day of the competition, only 4 students can be representing your school during the oral presentation and during the physical test. You can have less than 4, but there's only 2, that's fine. The other students, they can come and attend, they can be cheerleaders, they can cheer them on, they can watch the oral presentation, they can watch the physical test, they can play support roles to help move things or carry things. But additional teachers and parents are all welcome on the day of the competition, but only the 4 will be involved on that particular day. Later I'll follow up on details on transportation for the day, whether you're going to need transportation or not need transportation. So we do provide bus transportation if needed. We provide lunch on that day as well. So, and those details then will be coming. So I'll be putting PDF documents on the web page that will have all the details for the technical paper, the details for the oral presentation, and after today we'll be putting up a document that'll kind of in more detail talk about the actual physical test as well. Okay, so what I'm going to do first is show a video of last year's competition and the Wall of Wind. So the first thing I'll do is show the Wall of Wind.
Here at FIU Engineering Center, our faculty and students are engaged in research that is impactful. Our faculty and students and the entire world an opportunity to...
Okay, Dan, we're going to stop the video for just a second.
facilities, buildings, and structures that...
So 5, 4, 3, 2, 1. Okay, now we're going to show the video, which is also on the website too. A general video just about
Here at FIU Engineering Center, our faculty and students are engaged in research that is impactful. This particular facility here gives our faculty and students and the entire world an opportunity to develop the type of facilities, buildings, and structures that would be resilient to the impact of hurricanes.
The Wall of Wind project started 6-7 years back here at FIU with IHRC and College of Engineering and Computing. The goal was to recreate or simulate hurricanes so that we can study the damage modes and try to build better.
The whole thing about the wind engineering team here at FIU is we started basically with going out to storms and measuring the wind field in the storms to better understand the characteristics of a hurricane. Once that was done, they wanted to find out how do we bring the hurricane to the lab so we don't have to go to the storm all the time. So they developed the 2-fan wall of wind in 2005. From there, people got excited. We got private funding for the building and for the 6-fan wall of wind. And then once we developed the 6-fan, we were able to get a lot more characteristics of a hurricane. Typically, what you'll hear about wind separation, and people are like, "What is wind separation?" And it's when the wind, typically when it goes over a building, you get a separation point, and you get a lot of lifting force at the eaves or at the edges of the building, and that's typically where the buildings are more reinforced. And you usually don't see that. This is wind. But when we do testing here with wind and wind-driven rain, you can actually see the water going over and you actually visually see what you read in the book.
Well, the long-term impact is basically we should come up with research that can develop mitigation devices, that can develop stronger products, that can enhance the building codes, that can change the perception of human beings about the impact of the hurricanes. So the biggest impact that we want to make is achieve a hurricane resilient community. We don't want things to happen that happened 20 years back when Hurricane Andrew hit South Florida, and that's the goal, that if there is a future Hurricane Andrew, we shouldn't go through that much of trauma or that much of damage that we had before. So if we can achieve that, I think we have achieved what we needed to.
Okay, now I'll show you a video from last year's Wall of Wind Challenge. Well, the Wall of Wind Challenge is all about wind engineering and mitigation. So what we have here today is we have teams of high school students from Miami-Dade County that have come here today to test their very own projects against the Wall of Wind. What's interesting, we decided to take a project that would simulate a one-story building with a flat roof, because there's problems with flat rooftops. When a hurricane wind blows across it, you have uplift. So we thought, let's have the high school students try and come up with a way to bring down that uplift.
This is really an outstanding project. I mean, I'm a meteorologist, but I learned a long, long time ago that it's not all about the forecast. And to see these high school students coming up with these ideas on how to mitigate buildings, and in the long run that'll keep people safe and save a lot of money in the long run.
Watching it go through the test was pretty nerve-wracking, not gonna lie. We saw our project start to wobble at around 60 miles per hour and then kind of tore off one of the walls, so we saw all of our work kind of be destroyed, but at the same time succeed since none of the gravel was moved.
I think it really brings about ingenuity. It taps the young minds on different ways of looking at decade-old problems and situations that new ideas might be worth pursuing.
First place of this year's 2013 Mitigation Challenge,
Coral Park High School.
The watching the wind speed increase, I started to notice little parts move, and I started getting nervous. But after everything went through, everything held together, and there was no gravel moved, or everything worked the way it was supposed to work. It was really something.
And next year I will be attending FIU. I will be starting as a mechanical engineer.
Okay, so as we saw from the video, last year's project, again, it had to deal with a flat roof challenge. Well, we've now come up with a different challenge, and so now Dr. Zies has come up and talk about this year's challenge and some of the science and engineering behind the topic as well. Sorry. Start.
So, hi everybody, and welcome at FIU. What I'm gonna do today with this presentation is try to give you a little bit like the background of wind engineering, some basic knowledge, which may help you during this process of participating in the Wall of Wind Challenge. And I have also like 2 or 3 slides that we added at the end related to this year's challenge. So, as you can see here, wind engineering is part of civil engineering. We have different disciplines in engineering, and civil engineering has different components. It could be geotechnical, it could be transportation. We deal with structural engineering. What wind engineering is a combination of structural and environmental wind engineering. So there are different applications related to environmental issues or structures and buildings. I like to use this slide because wind can be a friend and can be an enemy. Unfortunately, in this part of the world, we deal more with these kind of like photos. So we have been using wind to our advantage, but at the same time, we have some really extreme wind events that create a lot of disasters, big disasters and casualties. If we try to define wind engineering, we can describe it as a rational treatment of interaction between wind in the atmosphere, the atmospheric boundary layer, and man and his works on the surface of the Earth. So the basic difference between civil engineering applications and aeronautical engineering applications, because a lot of people are confused about wind engineering when they hear about wind tunnels. Civil engineers, they deal with wind effects on the lower part of the atmosphere, the effect on the structures and the buildings and and people as well. Whereas aeronautical engineering is further up in the atmosphere. So we deal with the lower part of the atmospheric boundary layer. It's a synthesis of knowledge from fluid mechanics, meteorology, structural mechanics and dynamics, and physiology. And aerodynamics is important, but it's not as critical as in aeronautical type of like problems. Now I have a lot of information here, but what is important for you to understand is this distribution, which we call it the mean wind speed profile. That's how the wind changes with respect to the height, starting from zero height, the lower part of the atmosphere at the ground level, and going further up. So we have the structures and buildings at this portion of the atmosphere, at the ground, and as you can see, the mean wind speed starts from 0, and as we increase the height, it reaches a maximum wind speed, which we call it the gradient wind speed. Above that height, the profile remains constant, so we have more or less the same wind speed. What is important to understand is that the higher we go, the higher the mean wind speed. This is a typical record of wind speed with respect to time, and as you can see, there are a lot of fluctuations. So this is another characteristic of natural wind. It's not a constant wind speed. We have fluctuations, and we're particularly interested on these spikes over here, what we call wind gusts. That's what we use when we design structures. And another term that we use to describe these fluctuations with respect to the time is turbulence. So turbulence is a very important characteristic of the wind that we need to consider when we design buildings. Now back to the profile, the one that I showed you before. When we have this kind of distribution, we have our building, the structure that we need to design. How we translate that into an actual force, a simplified, oversimplified way to do that is to assume that we have the equivalent wind-induced force applied at a certain location of the building. Of course, there is a relationship between the magnitude of this force and the actual wind speed. And then by applying this force on the surface of the building, we come up with certain reactions. There is a shear force, an overturning moment that we use to design foundation or other components on a structure. But, of course, it's not that simple. There is more into that, and that's what wind engineers do. Now we go into fluid mechanics that I mentioned before. We have what we call the streamline object, which is the first one, and then we have bluff bodies. Buildings are bluff bodies. Their shape is not streamlined. It's not as easy for the wind to go around these structures. And that is what creates additional force, a more complicated kind of interaction between the wind and the structure, which we need to consider in order to come up with more precise recommendations. Here we have another example of an actual building. It's a low-rise or mid-rise flat roof building. So this is a bluff body, and we have the wind approaching from this direction. And then the interaction starts, and we have certain characteristics, certain type of forces applied on the structure related to the wind flow. So you see that this is what we call the windward phase, the one that hits the phase that experiences positive pressure because of the wind. And then the wind flow goes over the building, and at this location here, we have a flow separation. The flow is detached from the surface, and that creates a negative pressure. That's why we have all these uplift forces on the roof of the buildings. Depending on the dimension of the building, we may have a reattachment, and when the flow reattaches, we go back to positive pressure. So there is a lot of different phenomena that happens when the wind flows around the building. And this is what we try to examine in order to provide a detailed picture of the pressure applied on the building. Now, this is something that we use very often, and that's what the building code has. So yeah, here we have the pressure coefficient, and that's what we get from the building codes. This is a normalized way to present the wind-induced pressure. So we have the CP, which is the pressure coefficient, delta P is the design pressure, and we divide that by the dynamic pressure. This is a normalized, a non-dimensional way to present the applied pressure, and when you use a building code, you can have access to different values for different cases, different kind of buildings, and get the pressure coefficients. Now, some common features of pressure distribution on buildings. This is the general case if we want to kind of group the effects of wind on different structures. In general, pressures over the front face, the windward face, are positive and reduce rapidly as the flow accelerates around the side. So when you go towards the corner, you have lower pressures. pressure decrease downwards along the face center. So we have the stagnation point, which is approximately at the 70% of the total height, and that's the maximum pressure the windward side experiences. And then around that stagnation point, we have smaller pressures. Pressures on the rear face, the leeward side of the building, are in general negative, and roof and side pressures are mostly negative with very large localized suctions. And those are the areas closer to the eaves or the ridge of the roof. That is the critical, actually, like suction that the facade, the building envelope experiences. Now we said, you saw before the record of pressure with respect of the wind speed with respect to time, and you see there that we have certain fluctuation. The same applies for the forces. When the force is applied on the wind-induced force applied on the building, this fluctuates. It's not a constant force. So fluctuating forces on black bodies may be caused by the natural turbulence in the flow, the fluctuations in the wind speed. We may have an unsteady flow caused by wind moving around the body itself, which means that although we have the fluctuations on the wind speed, at the same time there is interaction between the flow and the actual structure, which upsets the flow, and that gives additional fluctuations in the forces applied. And the last one is the fluctuating forces when the building starts moving. If we have a flexible structure, that creates additional fluctuations. So you realize that in order to define the force applied on a certain structure, it requires a lot of testing, and we need to know a lot of details in order to be able to get an accurate picture of the wind-induced forces. So if there are fluctuating forces on buildings, how we determine the wind loads? What do we need to do as engineers, wind engineers? The first thing an engineer does is to consult the building code or the wind standards. So you have a certain structure, you use a certain building code depending on the location you are. You have local or national or international building codes, and you try to identify the case that represents the building that you want to design. Unfortunately, this is a simple process when it comes to residential structures, common shapes, simple shapes. But when you have special structures like very high, very tall buildings, or a bridge, or a stadium, or something that is very specific, a very specific structure, then you can't find recommendation in a building code. You have to do a special study, which is a wind tunnel study. We have the boundary layer wind tunnels, and we call them boundary layer for the reason I explained in the first slide. That's what civil engineers use. This is different. It's a different wind tunnel than those aeronautical mechanical engineers use to study the wind interaction with planes, airplanes, and aircrafts. So we have the boundary layer wind tunnels, and we make a model of the structure we want to test. We place it in the wind tunnel, and we examine the wind-induced response of the structure. I have two examples here, two pictures. You can see the boundary layer wind tunnel. Wind is approaching from the rear end of the tunnel. We have those small elements here, we call them roughness elements, to create the atmospheric, realistic atmospheric boundary layer. That introduces turbulence and also creates the profile, the logarithmic profile that we need in this type of studies. And you place your model, the structure, the building model, on the test section. This is equipped with a turntable. We can rotate and examine different angles. And of course you can add additional buildings, the surroundings, trees, or other buildings that are close in the proximity. That was an experimental approach. At the same time, we have computers. So we use what we call computational fluid dynamics modeling, CFD modeling. You can use a computer, add those characteristics of the building, the geometric characteristics of the structure, the surroundings, or whatever is considered important, and do the analysis numerically. At this point, it's not yet as advanced. For certain type of studies, we get adequate results, but still it requires more experience, it requires more time in order to come up with precise wind loading results. And this is another approach, and that's what we have here at FIU, large scale or full scale facilities. Wind tunnels, we test something that's really small, geometric scale of 1 to 200, so you scale down 200 times, 100 times the structure. The advantage of these facilities is that we can test real scale, full scale components, or even like large scale buildings, 1 to 5, only like 5 times smaller. And this is a major advantage. This is the wall of wind, the 12-fan wall of wind, as you can see. And it's more or less the same concept. We have a test section, we have a turntable, and we place the model in front of the wall of wind, and we try to extract different type of information, pressures, forces, or other effects, deformations. So we have the wind loads on the building. Is that all we need to design the building? In certain cases, yes, that's sufficient, but at the same time, we try to advance the knowledge. We try to improve our understanding of this wind structure interaction. So there are different things that we can do. These are some examples of residential structures, low-rise buildings, and we have also those very specific structures, the super tall buildings that we see around the world right now. We can add certain components to reduce the load. For example, we know that the roof experiences very high suctions. We have seen a lot of damage on the roof of a residential structure. We can come up with certain architectural features that we can add in order to reduce this load. This is one example. At the same time, we have these structures that are very, as I said, very specific cases. We test them in the wind tunnel, and then certain changes can reduce the total cost on the design of the structure. So we come up with different geometric features. We change the corners, we chamfer the corners, and that helps to reduce the wind-induced effects. This is one of the examples, the Type A 101, one of the tallest buildings right now in the world. So this is like kind of like a simplified representation, but it shows like the effect of the advantage of doing a detailed wind tunnel study. This was the original design. This is a plan of use, so we had a square kind of like shape, and just by chamfering the corners, cutting pieces from the corner, the four corners, the team managed to reduce 25% of the total base moment. And when we're talking for a building that is 1,000, what is the total height? I don't have it here, but 101 floors, we're talking for a huge, huge cost reduction just by reducing, by changing the shape of the layout, the corners, and reducing to 1 to 3/4 of the total cost and the base moment. And we go to this year's challenge. These are the slides that Dr. Erwin is also like a member of our team. He prepared, and this year what we decided to do is what we call shape optimization. So you're gonna have certain building, certain directions on the building, certain restriction on the building shape, and you need to come up with different modification, different shapes in order to reduce the total force applied on this structure. How we're going to examine that, how we're going to test this. You're going to have a tall building. This is going to be a building model which we're going to place in front of the wall of wind. We're going to provide you with certain specifications, the total weight of the building, limitations on the dimension of the building. These will be transferred to you by Eric. He's going to post it on the internet and give you like more details on the shape restrictions or the weight restrictions. we have also some other restrictions regarding the center of gravity. So you're going to need to follow certain rules, simple rules, nothing complicated. We just have these rules to make sure that we test similar cases, and we're going to place this building, this model in front of the wall of wind. We're going to have this stop over here, this block, to prevent sliding. And as we turn on the wall of wind, the fans, the force starts, we have a certain force at the building. So at a certain wind speed, we will have the model tipping, like turning over. Depending on the shape of the building, depending on the modification you do on the size, on the shape of the building, this wind speed is going to be different. So what we're trying to do here is to see which team will come up with the best design in order to achieve like the highest wind speed. And the model will be will stand and withstand the highest wind speed, and that would be the best design case. Now, the total height, I'm going to just briefly go through the different like restrictions that we're going to have. The total height will be 32 inches. We're going to have a square base, which we provide. We will send it to you. This is going to be, I think, 8 by 8 inches. But as I said, you're going to receive details about the design of the model through the website. And then you can build your model on top of that base, of the square base. You can change the shape. That's actually what we want you to do, to come up with the ideal shape in order to achieve the highest wind speed. We have the two base dimensions A and B. The restriction is that B must be greater than 8 inches and A must be less than 2 times B. So if we assume that you select B equal to 8 inches, then the other dimension must be up to 16 inches. Then we have a total weight of 30 pounds. You need to make sure that you don't exceed that weight, up to 30 pounds. This is a very important detail. And we want you to have the center of gravity 4 inches upwind of the stop. So if we assume that this is the windward side and we have also the leeward side here, this is the stop, the center of gravity must be at least 4 inches on the windward side. So more or less at the center, if we assume an 8-inch width. Now, if you have questions on how to come up with this design, we can help you. You can send us emails. We can tell you how to roughly estimate the location of the center of gravity. You can send the questions to Eric, and he's gonna we're gonna discuss them and get back to you. Let me see if there is anything else that I have here. No, we can continue with the next slide. Here there is a lot of text. I'm not gonna go through that, but you can find the description of the contents. It describes the procedure we're gonna follow, how we're gonna test the model you're gonna bring to the wall of wind. It has details on the weight, it has details on the dimensions, and all this information that you're gonna need to use and follow before we start the test. Now, we have some additional restrictions, and we decided to add that because we want you to come up with something that is kind of like uniform along the height. There will be certain restrictions on the openings, just to make sure that more or less all teams have the same amount of openings on on the surface of the building. Shape can be anything, but must always have minimum solid width of 8 inches. And I want to like make sure you understand that there must be a solid component which has to be at least 8 inches. The center of gravity must be directly above center of square base. I already went through this. I explained that already. And as I said, this is something that we can give you some advice on. Like if you have questions, we can like help you with that. And the base that we're going to provide to you has a total height of 2 inches. The stop on the rear end will be half inch. And you have to start building your structure above the 2-inch base. Let me see, is there anything else? No, we have the same component. So here you can see some examples. As you can see, all 4 of them are solid structures, so this is important. This is similar to the example I showed you before with type A1-1, change the corners. That will have an effect on the total force, on the total wind induced force on the building. It could be like a circular section and different features on the perimeter, or even a triangular section. But all of them, they're solid pieces that need to have a minimum width of 8 inches. And I think that's the last slide. Yeah. So, questions, please send us your questions ahead of time. Make sure you follow the rules, and the sooner you ask, the better it is. So during the design process, during the conceptual phase, just email us if you're not sure about something. If something is not clear on what we have on the website, you send us the question and we'll try to reply as soon as possible. Thank you.
That's it, Dan.